All right, so this week we're pleased to have Fedong back. He's going to talk to us about the continuum limit of theta functions. So, Fedong.
Okay, let's go. So we'll begin with definition of the theta function. All right. Definition of theta function. Define this. So summation over all integer. Two pi I and 3 plus pi I em n. So Z is a vector, complex vector with also n, and this matrix B is a n by n matrix, and which is defined by the Riemann surface. So the theta function is corresponding to a Riemann surface, and the B matrix is the periodic matrix.
So two questions here. First, theta depends on B, yeah?
Theta is, of course, depend on B.
Okay.
So I'm just too lazy to write that. But,
second, so just a question about convention. So B has positive definite
yeah,
imaginary.
I didn't finish my B. So B is symmetric, and the imaginary part of B is positive definite. That's then all those things will guarantee this series will converge absolutely. Right? Okay. Now that's the theta function. And next we need to understand what is the continuum limit. So in a very simple word is when this n goes to
I'm sorry. I mean, you know.
Yeah.
Before we understand the continuum limit,
yes,
I think we should also understand. I mean,
the bracket.
Yeah. I mean, because it looks like a product of a sick mind without any explanation.
Okay.
You know.
Okay. Yes. So
I mean,
this. Yeah. Yes. The inner product is means M1 MJZJ. So J from 1 to n, and here the same. So B act on vector M is another vector, and the inner product. So is that clear?
It's not getting any healthier this way. I mean, it's not the notation. It's.
So your question is why consider or what?
Why would anyone think about it? And I mean, you know, some of us know and some of us don't.
Think about what? The theta function?
Just in general. So what's the purpose?
That's the yeah. I mean, after that, I will tell a story why we care about theta function. So now, why people care theta function? The story. So the solution to the KdV. So this KdV is like this. So the solution will depend on x, t, and epsilon. So actually, we call this semiclassical. And you can represent the solution by the theta function. So this is defined by the limit of epsilon go to 0 of uxt epsilon. So uxt epsilon solves a semiclassical KdV, but here this limit is in distributional sense because it will oscillating when epsilon go to 0. When you remove this dispersion term, it will become very strange. But this kind of distribution limit exists, and this limit you can represent it by the second derivative of the, why write this? Epsilon go to 0, epsilon square log theta. So that where we want to study this theta function. So this theta is what we define here. And that's the motivation. And now the object we want to study is this.
So a point of clarification.
Yeah.
So this the choice of theta function depends on the choice of what
The
spectrum you're
problem.
picking for the solution to KdV or what?
Yes, and I didn't specific what is Z and what is B in this theta function. And that's a very long story, and we're not going to talk about that. And I will formulate the problem just based on this theta function. So,
Sorry, Fadang, I also have a question.
yes.
So is U bar a solution to this equation you wrote above or to transport equation?
U bar is a semi-classical limit of the solution to this equation. So this
That's what's
is
so magic. That's what's so magic, Louis. You take this limit as epsilon goes to 0, and you end up with something that's not solution to transport equation anymore, because transport equation you learned is
no. It's not the transport equation. This
It's
is
Burger's equation.
Burger's equation.
Dima was calling it transport though.
But I mean, it's not go to the transport equation.
So it's weird, but it regularizes the solution is the thing.
But it's like a theorem developed during 1980s. So people started with Lux-Lavermont. So this theory is called the Lux-Lavermont theory, by the way. So Lux-Lavermont.
Well, it's still extremely unclear. First of all, so there is no quadratic form on the left in this limit, and there is a quadratic form in theta function. So where does that come from?
What
He's talking about the matrix.
Matrix B. I mean, you know, if you take different matrix, you get a different limit, obviously.
So yeah, the problem is here. This is a theta function I didn't define. What is theta function? Because it's related to the spectral problem for the KdV, and that's a long story. And we will totally ignore that. And I will state.
We have an hour.
So
Yes.
I think the point is that, so let me make sure I understand. So
Yeah.
different choices of B will give you different choices of solutions. So depending on the initial data you're given for this zero dispersion KdV or semi-classical KdV, will give you different Bs. But that's a part of the story you're trying to hide anyways, I think, yeah.
Okay. The foreign thing will make it clear. So what is this theta function to this KdV? So problem 16. So we consider a lattice or point on the unit interval. And it's denoted by eta 1 greater than eta 2. and greater than eta n. Now this n is dependent on a small parameter epsilon, and it will also go to 0. And there's a distribution. There's a density function to control the distribution of this lattice. So that's defined as following: minus pi epsilon over phi eta j plus little epsilon as epsilon go to 0, and eta 1 is 1. So phi eta is a continuous function defined on 0, 1, which is a density function.
Phi is given, yeah?
Yes, everything is given.
Okay.
And it's strictly positive. So that's the lattice. And from this, we can obviously get the number of the points in this interval, right? So this number of points is behaving like asymptotically, like this, which is very easy to figure out. And now, at each point of the lattice, we can define. We can choose the vectors now. They belong to what? Yeah. So Z is a complex vector, right? And the dimension of the vector is n epsilon, and Zj is defined by I Aj over pi epsilon. And what is Aj? Aj is a function A take value at eta j. So I will mention the function later. And now the B matrix, the diagonal of the B matrix is I gamma j over pi epsilon. And gamma j is also gamma take value at eta j. So this is a diagonal, and off diagonal we have Bjk equal to I over pi tau jk. And tau is another function with two variables. Tau jk is tau eta j eta k. And j not equal to k. So that's how we define the theta function. We have two things, right? Z and the B matrix. So that's how we define this, and the assumption on those functions. The first one is A eta and the gamma eta are continuous function on 0, 1, and gamma is strictly positive. Second is about this tau function. Tau eta mu is continuous, of course, and symmetric, and is kernel to a positive definite operator T. So T is this operator. T tau eta mu f mu. And this operator is a positive definite.
No, so I don't understand. What do you mean that the matrix is the kernel?
Tau is a function. The matrix is tau jk. Tau jk is take value at the grid.
So you define No,
So-
hold on. So
Tau JK is tau take. So you have the interval, right? And you have a lot of lattice. Now it's a two variable. So you basically,
I see. So you mean okay? So you mean integral kernel? Okay, fine.
Yeah.
Okay, so that clears it up.
you take out the values and basically that's how you get this tau matrix. And we also, so tau JK, this matrix is positive definite. Okay, so that's the problem setting. Let me circle this thing. So we have Z is here, and we have B is here.
So you're given, as of right now, at least A, gamma, and tau, correct?
A, gamma, tau, and the density function,
Fine. Okay.
which define the lattice, right? So now the problem is very clear. What is a continuous continuum limit? Is taking the epsilon go to 0. So I want to study the limit epsilon go to 0, epsilon square log theta z e.
So your claim is that this, with the appropriate choices of phi, A, gamma, and tau,
Yeah,
it is
this
solution to KDV, or with zero dispersion.
you can forget the KDV now.
But that's your claim, though. Yeah, that eventually, with the right choices of all these things, you get solution to zero dispersion.
All
KDV.
those function has basic meaning if you really want, but or not physical meaning, but it's from the spectral property or the spectral problem of the linear shading operator, and that's too much to talk. And
Sure, I can buy it. So
so the problem is clear. Let's take a look at the setting. So we have a density function and this vector Z and the matrix B. So when epsilon go to 0, we can see the number of the size of the B matrix growing, right? Growing to infinity by infinity matrix. So it's like a very complicated problem, sounds like, right? All right, that's the first page. Now, we can state the theorem. So first the theorem. Okay, before that, let me write down the theta function first. So theta function now become this. M is integer value, of course, and exponential minus phi epsilon. So this phi epsilon m is the following function 2 aj mj. So it's the quadratic form.
AJ or ZJs, yeah, I think. You said
What?
it somewhere. AJs or ZJs, yeah? Or what the taking the role of ZJs.
aj is yes.
Right, so scale the appropriate. Okay, I see. So
Yeah.
just get rid of the pi and the epsilon.
Yeah, so this I pi over epsilon is just to get rid of this pi and I. So everything looks like real on the exponential.
Yeah, okay.
But it's of course negative. So what's the second term? Second term is from this B matrix, and this is a diagonal. J from 1 to n epsilon, and plus the off diagonal terms. So what's that? It's epsilon square, tau jk, mj, mk. That's just a simply you substitute into the theta function by the function we defined above, right? Now theorem 1. Limit the leading behavior of this theta function is minus limit epsilon go to 0 of the minimizing problem of this phi epsilon.
The continuum version of it, yeah.
That's the discrete one.
Still discrete,
It's
but m is
discrete.
increasing, yeah. But it's okay. It's this looks familiar from random. It's just the saddle point approximation, more or less.
Oh, really? I don't know this connection, but
Yeah, exactly.
but of course the theorem seems very not too interesting because I believe everyone can do that because it's just some quadratic optimization problem, right? You can always find the minimum. So because this that's a leading behavior basically. So this epsilon square because go to 0 very fast, so you can actually ignore that. And this is positive, so the function will looks like this. Now, of course, this minimal, right? Intuitively.
It's exactly a saddle point. That's interesting. Okay.
Yeah, you can prove this is exactly is strictly convex, and proof will be skipped for this theorem 1 because not too much interest. So theorem 2. This let's denote this limit f. So f is also the, we can actually compute this limit as following: 1 over pi minimum of f in h phi f. Now it become a minimizing problem for a continuous version. So what is this function of phi? And you can take a guess from seeing this phi epsilon, but I believe you cannot easily guess a correct form.
Oh, sorry for that. What was H?
What I will define later.
Okay, sure.
The h is based on this function. So phi f is 2, 0, 1. So that's basically, since you have the density function to control this lattice, right? And eventually you will involve this density function. So it's a eta phi eta f eta e eta plus gamma eta phi eta. That's the magic part. 2 eta 2f squared eta minus f eta minus integer part of f eta minus 1/2 square plus 1 over 4 eta plus 1 over pi 1 phi eta phi mu tau eta mu f eta f mu. So this is a functional phi, and h is the space of this. F is measurable function in 0, 1, such that phi f is bounded. Okay, that's a cell on two.
Okay, so scroll
But-
back up like half an inch. If
Let's
I were to
take a-
just guessed, I would have guessed exactly what you wrote, but without that last piece. So without
without
f
this,
theta minus whatever that is. So the thing in the brackets, I would have just put f squared, and that would have been my guess for what the limit was. How crucial is this second piece? This f eta minus integer part f eta minus 1 half?
it's not crucial at all. It's like a small oscillating, but I mean, in general, it doesn't affect too much, but you still need that.
Okay, okay.
It's very small. It's between 0 and 1/4, the last piece.
Okay, it's
So
interesting. looking. I know you showed me this earlier, but I don't remember. I don't think I've ever seen anything like this, at least in.
so this
Right.
square bracket is the integer part. Okay, so you have the minimizing problem. Now, for theorem 2, I want to talk about a little bit about the proof. And the most important thing is how to construct this function.
So a second question.
Yeah,
If you just put f to be 0, I mean, you automatically have phi is minimized. So do you f to be fixed or something?
what f to be fixed? What
If I
do you
just
mean?
put f to be 0, then phi of f is, or phi of 0 is 0, yeah? Is that right? Or am I missing? Maybe not that second piece, yeah?
What? No. Okay. You need to compute this this limit. What do you mean? Oh, you want to find a minimizer?
I'm just saying to put f to be 0, but maybe not because of this
Well,
last.
it depends on this. Because
Right, but so I think the thing that breaks it is that this second piece with the quarter, the thing you've underlined in red. The
that
second
one doesn't really matter.
Yeah, but then you could just pick f to be 0, I think, yeah? Like the first
It could be
integral.
0. F equal to 0 is not the minimizer.
That's what I'm saying. So I think that comes from what's underlined in squiggly in red.
No, even if you don't have this, f equal to 0 is still not the minimizer.
Why not? You have 0 identically if f is 0.
No. It's this a is strictly positive. So if you
Yeah, but if you're
consider
multiplying
the
positive
graph,
function by 0, you get
it will
0.
be here. It's not like you cannot touch the.
No, you can't. I'm not. So a doesn't have to be 0, but if f is 0, then that's the integral 0, yeah?
Integral is
I integrate something against 0, I get 0. So that underline, the second underline part must be somehow relevant.
oh, wait. F equal to 0 give me. Let me think.
Without the squiggly part that you underlined, then no, 0 is not necessarily the minimizer. But
Hmm,
so I don't know, there's some subtlety, I think.
wait, that's the. It should be the minimizer. Yeah. Why if? Let me think.
So the curly braces, yeah, tell you that f is 0 is not necessarily.
Oh, no. Oh, okay. I almost forgot. A is any arbitrary function. It could be negative. So you don't know. It's not positive. Okay. Yeah, suddenly I forgot that.
It doesn't quite fix things still, but fine, I'll accept
No,
it.
no. If A is negative, then this linear term will give you some contribution. So the function will look like this. I mean,
No, but if f is 0, then that's it.
F0, but that's not the minimizer.
That's what I'm saying. So f0 is not a minimizer just because of the second term.
Not second term, because the first term, not the second.
The second, if f is 0, so ignore the middle term. If the middle, we'll talk later. I say that it's because of the second term that it can't be 0.
So what you said is just ignore this thing, right?
If you ignore that, then if I put 0, I automatically get 0.
Yeah, you got 0, but 0 is not the minimizer. Phi
I guess
can be
okay, so it could be
negative.
negative 2, yeah, is what you're
Yeah.
saying.
Yes,
Okay, so maybe I
Because-
agree then.
because A could be negative.
Okay, so the function itself doesn't have to be positive.
I didn't say that, right? I only say gamma is positive. A is just continuous function.
I guess so. I think I was assuming that this function was automatically positive because it
No,
seems
no, no. The function is not positive. It's bounded below. That's all we need.
is it obvious that it's, I guess, yeah, it is obvious that it's bounded below, but it's not bounded below by 0, I see.
Yeah, no, you cannot see that.
Okay, so that clarifies things then. Cool.
Right. So, okay. And so what we are going to, okay, I will talk about something related to the, how to find this phi. So the first question is how to, let's do it. Okay, we got time. And that's the important part. So we pick f from this space, right? And it's a measurable function over a compact set. We can find a pointwise approximation by rational valued simple function, right? So rational value converge to this. Simple function, I mean the piecewise continuous, piecewise function. And so without loss of generality, we assume f is a rational valued simple function, and we define if this in this way, p sigma plus alpha sigma d sigma, when eta in this interval, sigma is from 1 to, so assuming it has m values, m could be very, very large, right? And p sigma, alpha sigma, d sigma are integers. Now, we can also define this. J sigma is the index set J such that eta j belong to this interval. Now let's focus on this interval and let's see what it looks like. So, right, at this interval, the function f is just a constant. So it's p sigma plus alpha sigma d sigma. Now I define mj. So when you fix epsilon, m is belong to a vector. So m is belong to a vector z to the in epsilon, and mj is defined as following. What is p sigma plus 1? For the first. So this means the number of the number of the elements in this set. So the first, this number of indices to be defined by this, and the next e sigma minus alpha sigma. So the next, this number of index defined by the integer below that. So in this picture, we can see This is a P sigma plus 1. This is P sigma. So here we have a lot of eta j's, right? Each eta j we can define mj. So it's clear about the definition so far?
So far, so good, I think.
Okay. Now, since now this it's just a bunch of points on the this m is a vector which is a point distributed on this 0, 1 interval, right? And we will construct a function f epsilon eta based on this mj. So you extend those points to a integer valued piecewise function, and when eta belong to that, so that means simply you, when this is eta j, then you open it, right? And you got a small piece, so it will become a lot of piece, and that's the function f epsilon. Now claim will converge to f eta weakly, i.e. f epsilon eta d mu. So here is epsilon go to 0, of course. So we'll go to, so this measure mu, let's assume it's absolutely continuous with respect to the Lebesgue measure. So this is a claim. And we can prove it very quick. So let's just focus on this small interval. The eta, right? It become 2p's. So it become what? The first this kind of number of indices is P sigma plus 1, right? And it will give you mu. Let's see this. It's the alpha sigma over d sigma, and plus P sigma. The rest is d sigma minus alpha sigma d sigma. And right, so here.
So you mean, oh, no, okay, that's, I see. It's just over the interval, yeah?
Yeah. It's a piecewise constant function. It's so.
Okay, so I think I see it, because what was the original function? Scroll up like half an inch, I think it was a page above.
So f is
It is
this,
defined like that. Okay, I see.
right?
Yeah.
So now this thing you can simplify to give you, and the rest is this and that's exactly, right? So of course, for the whole interval, you can prove that, and based on this, we can talk about back to theorem 1. So we can find the limit. This will go to the first term for the phi f. And the second one is mj squared. That means we actually need to compute what is this limit. So you can actually show it as epsilon go to 0 weakly. It will go to that very strange thing. So f minus f integer minus 1/2 square plus 1/4 d. So that's why where this thing comes from. All right. Any questions so far for that?
So I think that was the only technical part, was where that second, because the rest I think are more or less obvious. They follow from.
It's like a construction, pretty constructive, right?
Yes, that whole thing is like, I think it's the only thing that's
But after you look at his construction, you feel it is very natural.
it would make sense in the context, I think, but it's the only thing that I think is technically involved. So the rest I think are obvious. If you
Yeah. So the rest, no. That's
comparatively.
the first step. So after that, we have 2 more questions you need to answer. The second, you need to figure out is this well defined? Means is it the minimal exists or not, and is it unique? And you can prove it is strict convex, and that's what you need to prove for that function. Once you get this function, that part is very simple, right? Fairly simple. It's also like 3 pages long proof. And we will skip this. The third one is we need to show this is actually this. So we need to show these 2 things are equal, which is not obvious. You have the limit, but doesn't mean it is exactly that limit of the discrete minimizing problem. So to prove that, we need 2 more claims. The first claim is giving any function in H, you can approximate from the discrete one. So exist m epsilon. So it will give you a sequence with index epsilon, right? Such that phi epsilon m epsilon will approximate phi f. This is the first claim. The second claim is you pick elements from the discrete problem. Then you can find f epsilon in the continuous problem such that limit inf this is non-negative, and these 2 claims will imply the the minimum of this continuous function is exactly the limit epsilon go to 0 phi minimum of this discrete problem. And that is also not trivial. So, but not going to talk about this exercise. Okay. So after this two theorem, and we have connected the leading behavior of the theta function to a minimizing problem. Now let's take a look at this. Okay, with this function phi, right? And we can find the variational derivative. So the first variation of this function is, so let me say theorem 3. Is actually the following: a plus t phi f plus gamma, the integer value, plus 1/2 gamma. When f is not integer. If it is integer, then we have a plus t phi f plus gamma f integer plus 1/2 gamma belong to 0 and gamma. If f is integer. So this is the variational condition. And which is a singular integral equation, right? This t now, it's not necessarily singular, but now makes sense more interesting.
Well, it's already weird. You have this like
It is weird. It is weird.
integer condition.
That's the problem. So let's compare this thing with the more familiar integral equation, which will connect to the logarithm potential. So this t in the KdV the KdV case, this t is actually the green potential. So log, what is our variable? Tf eta is maybe a minus. I cannot remember. E mu. I think it should be the
Gamma is R or what?
What?
What is gamma?
Gamma is some contour.
Unspecified or?
Could be the support of this measure, but it's so you can think of this as the imaginary. So gamma is belong to the pure imaginary axis.
Okay.
So that's for the that's actually not for the KdV case. KdV gamma is the real line, belong to the real line. But for nonlinear shading equation, for the Foxing nonlinear shading equation, it will be not the real line. But that's just give you the favor of the problem. So now it involves the logarithm potential, and we also have the classic problem. So let me think. And the following equation is from the paper by Turbitz and Kula. They are talking the existence uniqueness about the following equation. Mu w d lambda dw. So they are studying this problem, and these two. So the equation from the Venakides, this continuum limit of theta function is very close to that. So here we need to. There's some transformation between this. So phi f is simply becoming u, and gamma is sigma phi. So by this transformation, you can relate to this two equation. But here we involve this integer value. And the question which we try to figure out is how does this integer value affect this kind of existence or uniqueness? And another question is how can you construct a solution to the equation like this? So that's basically what I want to talk today. Question time.
So I have one actually.
Uh-huh.
So it's, what is my question? I guess it's so strange. It's integer. So did Venakides himself find any solutions? Like an actual, like given a, given phi, given f, or not given f, I guess, but given everything, can you actually find particular solution?
I mean, for this equation, of course you can. For some particular case, in general you can't. It's
Yeah, in
too
general,
hard.
you know.
It depends on the counter, and so if the counter is very strange, you can never find a good solution, of course.
So it's weird. It's like a,
Yes, but these two equations are not too far from each other. The only difference is this integer value, which is like a little oscillation, a little perturbation to the original function.
to me, I can't even make sense of what it means, I guess, why there should integer part should appear.
No, integer value simply makes the function become piecewise constant function. It's like a stairs, right?
Yeah, I agree. But it's I don't know. It still seems strange, I guess. Because I mean, what is it's supposed to be representing? What this is dominant contribution to.
The theta function. So okay, back to the original problem is we want to
Describe
study
KdV zero
the
dispersion,
behavior.
something zero dispersion. Yeah.
Of course, I mean, in the KdV case, yes, we want to study the small dispersion limit.
So I'm trying to think physically what it actually means for there to be these gaps. Is it like correcting for? I don't know.
I don't know. We try to figure out the physical meaning too. Is it I never saw any variational problem which involved this integer part.
Neither have I besides this one. So
yeah, I wish you have some like example in physics, probably.
I don't know. I mean, I have to ask Rosman or something. Maybe Rachmaninoff would know. Would ask him later.
Yeah, I mean, eventually this problem is some like logarithm potential and minimizing energy, right?
But with like a weird twist, I guess.
Yes, bit.
But interesting.
You still can talk about the existence and uniqueness, right? Maybe
Yeah,
not uniqueness, because this integer value will make trouble.
but existence for sure. Yeah.
I don't know. How do you know?
I don't, but it seems like it maybe shouldn't affect too much.
Also, there's another way, like you can use the solution to this problem to construct a solution. Artificially, you make some function gamma a and phi. So
it's weird, but it's interesting, I guess. So I think that concludes my questions. Any questions from anyone else?
Yes, I do have some questions.
Yeah.
So I think this is really good. I think some analysis part of the the integral theory. So I have a question about actually at the starting point, you use capital N epsilon, right? This capital N epsilon is probably is the number of the solitons, right? For associated with given initial data to the given.
Yes.
Can be presented by, I think, is your capital phi function, I think.
Capital F.
Capital F
So-
function could be take the I think as at a small f equals 0, then you can compute capital phi f and then capital phi, and then you can present this. This is actually how many solitons associated with the given initial data. So you need to specify what kind of initial data. Otherwise, what is your xt epsilon? We don't know.
Exactly. That's of course. So in the if you want initial data, we can take initial data like.
You have to specify the space and what kind of initial data, and you can present the solution. And this is the whole, actually, this analysis you're talking about today is based on the potential of n solitons by either by theta function or by the inverse scaling transform. Otherwise, this is one soliton. You just write down one soliton. So otherwise,
so if n,
otherwise, analysis you cannot do it. You cannot link the semiclassical limit or small dispersion limit to the minimum problem variation problem. So generally,
it's also Lattice paper.
Yeah, this is my, I think, guessing anyway. So initial data is very important as well.
So you need to
you have different
initial data which give you refraction less.
You may not have existence even for the all time. KDV. So KDV is nonlinear.
No.
Global existence actually has a
the
problem.
limit is not exist in general sense, but it exists in weak sense.
For the T, how can you control the T?
Uh,
Over the finite interval, or for the whole future time, or
so for KDV, actually, I don't know about the semi-classical limit.
You have confined to the finite interval for the T, I think. For the long time, definitely will be limit. There will be different. I think you have two limits here. Saying how can we exchange two limits? Problem one is with epsilon, other with T. So anyway, a lot of analysis, which is beautiful. I really
yes.
We don't do much about it. This is really just very pure analysis.
The paper is 1989.
Oh, I see. That some new.
It's very old.
Yes. Levermore did also similar problem to present the small dispersion limit of KDV equation.
Yes, that was a question I had actually, Fudong. Do you know what's in Levermore's paper?
What is the question?
You know,
Lax and Levermore. Well, maybe
the author.
It's a Levermore's dissertation. I believe it's like let me check.
So I'm wondering, because you can obtain solutions to KDV zero dispersion from that, but this is like a different class of KDV zero dispersion solutions. How do they compare? I guess I don't know if that's a sensible question. It might be.
That's the standard semi-classical limit. What do you mean?
Say again? Yeah, I know that's what I'm saying. So Lax-Levermore's semi-classical limit, yeah?
Yes. So Lax-Levermore, they talk about the potential is like this. But in this setting, since we're talking about, we're actually talking about a periodic initial data.
So it's different class of solutions, yeah?
It's different.
I see. Okay.
Because in their case, so in the Lax-Levermore, they can. Okay, so that's a two view of this problem. If you talk about semi-classical limit, so Lax-Levermore, they are doing the n soliton solution when n go to infinity. What the solution will behave? And in the Venakides situation is talking about the periodic initial data, and they talk about the finite gap solution. So when the gaps go to infinity, it's
number of gaps, and you shrink the size of the gaps. So this
yes, but when the number of the gap go to infinity, the the length, the length of
Yeah.
the gap is shrink.
It's this weird problem. Yeah, I remember. Okay.
Yes, yes. And but they actually both go to something similar, maybe which nowadays people call Solton gas.
That's right, because those two classes of solution can be presented by theta function.
Yes, yes.
You cannot
But
present by theta function.
the ratio of the theta functions, right?
So you have to study geometric algebra solution for for more general initial data problem. And actually, I have a question here. So in the KdV equation, the dispersion in front of the dispersion term, we put epsilon square. How is this very important, right? While you're doing analysis, right?
So
can you put the epsilon cubic or cubic something?
maybe, but maybe doesn't make sense because this is like a from standard the modulation theorem. So if we talk about, okay, this I can explain. So the original KdV is am I right? Right. That's the original KdV. Then we do the modulation.
Oh, that's come from the actually, yeah.
Then so you introduce those small variable.
Yes, small.
And then you will get the semiclassical. Because you replace this, eventually you will get.
Rhythm theorem, yeah.
Yeah.
But we can take some other variable. For
Of
example,
course, you can put arbitrary.
a small here, MN, yeah, absolutely.
But then it will give you something different. But I don't know what's
very difficult. I think another
Yes.
problem. More difficult. Some difficult problem. No, thank you.
Yes.
Okay. So any other questions? If not, then let's thank our speaker. Where's the clapping button? It's reactions, clapping. There we go. So I'll stop the recording really quick.